Hi friends, welcome back to the channel. Today we will be doing a problem from the topic of mechanical vibration. This particular problem was asked in GATE, Graduate Aptitude Test in Engineering, a test conducted here in India for the postgraduate admissions. This question is quite interesting because of a few reasons, because this is not a typical problem that we come across. So here, as you can see, there are two masses, then they are connected together with a spring. Nothing new. But there is something interesting about this problem. Before I discuss about that particular aspect, let's discuss or let me take you through a thought experiment. So as shown over here, in this case you have a mass and then it is attached to the wall using a spring, and then we have a mass kept on the floor as it is, no springs attached to it, so it is just kept as it is. So in the first case A and case B is case 2, think of imparting an initial excitation to the system in both the scenarios, both in case A and case B as well. What will happen? See, you expect vibration to happen in this case because there is a stiffness or there is a spring that is attached to the mass from the wall. Okay, so we expect this particular mass to vibrate after the initial excitation. But what happens when you give an initial excitation? By initial excitation I mean an initial displacement or an initial velocity. So if I give an initial velocity or initial displacement for this particular system, okay, the B system, then it won't vibrate because there is no stiffness here. Okay, so in order to have vibrations or in order to have an oscillatory motion, you need certain restraints in this form and you need certain stiffness, okay, and mass is obviously required. Make sense? Now let's go to the second thought experiment. See, here the first question that we should answer is how many degrees of freedom are there? So degrees of freedom are the independent quantities which are required to completely define the state or the configuration of a system. In this scenario, let's call the displacement of mass, this first mass, as x1 and this mass as x2. Okay, in this scenario, think of a case or a situation where I know x1 alone. If I know x1 alone, then x2 can take any value. But if I know both x1 and x2, it kind of helps me to determine the configuration of the system completely. Make sense? So that's why it is a 2 degree of freedom system. In a nutshell, if you know x1 alone, that is not sufficient to completely define the state of the system. You should be knowing both x1 and x2. So pressing forward, the same kind of argument holds true for the system shown in this figure, in the D figure as well. It holds true. But here you can see this restraint is missing. This particular restraint which was holding these two wagons or these two individual masses to the left hand side is missing here. Okay, so once I give initial excitation to this system, there are two possibilities. Now I am talking about the system over here, which is having more resemblance to the system given in our problem, or it is the exact system which is given in the question. Okay, So here when I give an initial excitation, there are two possibilities. Case 1, this whole system can translate. Okay, why it is translating? Because there are no restraints over here, no constraints over here, so that's why it is moving. Make sense? Then what happens? Then there is another possibility where let's call this mass as m1 and this mass as m2. Then m2 can vibrate with respect to m1 and m1 can vibrate with respect to m2. So these are all possible scenarios. Okay, so before diving deep into the mathematics of things, the key difference between this system and this system is that here translation is possible, rigid body translation is possible. By rigid body translation, I mean to say that there won't be any change in the relative position of these two masses. It can translate as it is. That is one kind of motion which is possible for this system, but it is not possible for this system. Make sense? Because it is fixed in space. Now, in the question they are asking you to compute the natural frequencies of this system. The system is a 2 degree of freedom system. So the first thing you have to do is come up with the governing equations of motion. Pretty straightforward. So going ahead or pressing forward. So the key takeaways are this system can have unrestrained translations. To be very particular, it can have rigid body translations. And the second point is that, but it can have rigid body translation, but at the same time, either mass 1 or mass 2 can vibrate with respect to the other mass. Make sense? Okay. Now let's go ahead and write the equilibrium equations or the equations that govern the motion of the system. So here as you can see, I am taking this as x1 and this as x2, and for the time being I think or I assume that this particular spring is in tension. So this will be the free body diagrams corresponding to the mass m and mass m shown on the left and the right as well. So now I have to write the governing equations of motion. So for this mass times acceleration is equal to the net force acting along this direction. See, I took x1 to be positive in this direction, x2 to be positive in this direction. So as you can see over here, there is a force acting on this left hand side mass along the positive x1 direction. That is why here there is a positive sign. I didn't put a negative there because it is actually along the positive direction of little x1. Make sense? And that force is k times x2 minus x1. I assume that the spring is in tension. That's why x2 is greater than x1. That's why the tensile force in the spring is assumed to be k times x2 minus x1. Make sense? Good. Now, similarly, going with the same argument for the right hand side mass also. So this is our right hand side mass. So going with the same theory, now for that, the external force acting on that particular mass is opposite to the direction in which I have defined my positive x2. My positive x2 is directed towards here, but the force acting at this mass is along the left hand side given by k times x2 minus x1. Make sense? Okay. So here we are. So these two are the final equations that govern the system of motion. So these two are two simultaneous ordinary differential equations that should be solved simultaneously to get how x1 is evolving with respect to time and how x2 is evolving with respect to time. But in this particular problem, our interest is not to study the evolution of these quantities with respect to time, but on the other hand we are asked to compute the natural frequencies of the system. In order to compute the natural frequencies of the system, we should solve the free vibration problem. Free vibration problem is nothing but a scenario where you don't have any external forces acting on your system, but you're simply giving an initial excitation and then leaving the system as it is. Make sense? So the key concepts is this one. I already explained it. So when a system is set into vibration with an initial excitation, it will vibrate with its natural frequency. So we need to compute those frequencies. Make sense? So for the time being, if you wonder why we have zeros on the right hand side, the reason is pretty simple. Because we are solving a free vibration problem. We are not solving a forced vibration problem. If we are doing a forced vibration problem, we would have got some terms coming onto the right hand side, f1 or f2, something of that sort. In order to solve it, there are plenty of ways, but I think this seems good for this situation. You can assume that little x1 varies like this. Let's see, this omega is an assumed quantity. We are thinking like omega is the natural frequency. We are a priori we are assuming that. That's why this omega is there, and phi 1, it is the phase with which mass 1 is vibrating, and phi 2 is the phase with which the mass 2 is vibrating, and capital X1 and capital X2 are the amplitudes of motion. Make sense? Now the rest of things are fairly straightforward. See this omega, be very careful. We don't know this omega, but we know that once it is subjected to initial excitation, it will vibrate at one single frequency, which will be the natural frequency of the system. And don't worry about the cos or the sines. You can take sine also, but the results won't differ. Then rest of the things are simply plug and check. You need to turn the mathematical crank with a bit of care, because otherwise you may end up with the wrong answer. So substituting for x1 double dot and x2 double dot, which are the derivatives of double derivative of x1 with respect to time, you will get these two quantities. Once you plug them back to the two equations that we had written over there, then we arrive here. Again, straightforward. Once we put those in a matrix form, it looks something like this. So here we have a system of two equations, linear equations. They are linear. We don't have an x1 square sitting in this expression. We don't have an x2 square sitting in this expression. So they are homogeneous and they are linear. Now, when you have a homogeneous linear system of equations, and if you want a non-trivial solution, then you may ask me, what is a trivial solution? See, trivial solution is straightforward. If x1 is equal to 0 and if x2 is equal to 0, that's a trivial solution. That will satisfy this set of equation irrespective of what is the coefficients over here. But I'm talking about, can I have a non-trivial solution? So in order to have a non-trivial solution for a set of homogeneous equation, the determinant of the coefficient matrix should be 0. So the determinant of this particular matrix should be 0. Make sense? So now if I take the determinant of that equation, I think there is a small mishap here. Yeah, I think that will do good. Okay, so if I take the determinant of that particular matrix, then I will reach somewhere here. Then doing some rearrangement, I reach here. The product of two terms is equal to 0. So either this quantity can assume a value of 0 or this quantity can assume a value of 0. So if you take m omega squared is equal to 0, that implies omega equal to 0. So the first natural frequency of the system is 0. There are two roots, and let me call this the omega 1 and let me call this the omega 2. So there are two natural frequencies of system. There are two natural frequencies for the system because this was a 2 degree of freedom system. If you have 3 degree of freedom system, then you will have 3 natural frequencies and then you will have 3 mode shapes also. Make sense? Good. So as one natural frequency turns out to be 0, it clearly indicates that the system is not vibrating or oscillating. The system can undergo a rigid body translation wherein there won't be any relative displacement between the two masses. Okay, so the key takeaway is that this kind of problem pertains or belongs to the section of 2 degree of freedom systems, which is not currently there in the syllabus for GATE, but this was asked back in 1999. And when you have a 2 degree of freedom system, there are two natural frequencies. How you find those natural frequencies? You write the equations of motion first, then you solve your free vibration problem, then you will get your natural frequencies. And this kind of systems wherein rigid body translation is possible, like the one we have just solved, they are called semi definite problems. They are called semi definite problems. Okay, so thanks a lot. Thanks for watching.